Science test is coming up fast, gotta make the good marks last. Looking at where we went wrong, get our knowledge super strong. Mr. Marsh says, time to learn from mistakes. Yeah, for good grades, whatever it takes. Yeah, feel the year 8 science power. Feel the year 8 science power. Woo, yeah. Mr. Marsh says, we got this.
Alright, so Claire's Court, Year 8 Science, CT2, 25-26. Put your name on it, put your form in it. It's a 50-minute paper. You've got to write your answers in blue or black ink, use a calculator. Always bring a calculator and always show your workings, because I can give you marks, or your teacher can give you marks whenever they mark. If you've got the calculations shown, even if you make a mistake. Let's look at question number 1. What organs do plants use to make food? Well, the process we're looking at is photosynthesis. So we've got flowers, roots, leaves or stems. Which bit is green? Which bit faces the sun? It's the leaves, because you need light for photosynthesis. What's the job of the roots then? Give a job of a plant root. Hold the plant in place. So that probably is useful. But also, they're there to absorb water, and they also absorb minerals from the soil, don't they? So any of those jobs that the roots do, which is more than one job, you only want one, but you could suggest any of those, and it'll give you the mark. Hold it in place, absorb water, or absorb minerals. Okay, easy. The diagram shows the human gas exchange system. Name the organs W, X, Y, or Z. Write the correct name for the organ next to the letters. Next to the letters. So we have, okay, right, let's look here. Which one should we do first? We've got the windpipe, the trachea. So we'll write trachea there. And then we've got, well, that's the lung, isn't it? Then at the bottom, Y, you can see the diaphragm. That's the bit that sort of flattens and increases the volume, reduces the pressure, causes air to go in. Okay, and then you've got one of the bronchuses. They're bronchi. There's two of them. Singular is a bronchus. On the mark scheme, it says do not accept other spellings. So misspellings are not allowed. You have to learn to spell it. So it's a bit of a spelling test as well. Question number 3. Give one reason why condensation is a physical change. Condensation, turning water vapour into water, is physical. It's not a chemical change. Well, it's still water. It's water vapour turning to water liquid. Because we don't make a new substance from it, it's not a chemical reaction. It's only a physical change. We can make it go backwards very easily, so it can be easily reversed. That's another clue, isn't it? Why is the combustion of hydrogen a chemical change? So we're burning it this time. Why is burning hydrogen? No new substance is formed. Wrong. There's a change of state. No. Heat energy is given out. Which, yes, but then you could do that with heat packs in PE. The reaction is hard to reverse. Now that is a very common question at Key Stage 3 about chemical reaction and physical change. Miranda starts running. How does her breathing rate change as she starts to run? Well, same way yours does. If you've ever gone for a run, you may know what's it doing. So it says how. Does it go slower? Does it stay the same? Or does it go faster? Well, your breathing rate goes faster. But then it says when she starts running, her pulse rate increases. What does the pulse tell you about what's happening inside the body? What does the pulse relate to? Well, it relates to the beating of the heart, doesn't it? Every time the heart squeezes the blood around your body, you can feel a pulse. So it tells you that her heart is beating faster inside her body. I hope that makes sense. Right, this is an alveoli picture from the lungs. Look, gas exchange happens in these air sacs. Which two gases are exchanged? It's not the gases that go in and out, but the gases that go into the blood and come out of the blood. Two of them. One goes in, one goes out. So we're looking at an exchange in the air sacs. Well, oxygen, carbon dioxide, nitrogen, oxygen, hydrogen, carbon dioxide, carbon dioxide. There's only one answer, isn't there? Oxygen and carbon dioxide. Describe two features that increase the speed of gas exchange in the air sacs. Now, if you've done your revision, you will remember that we've got these lovely thin walls that are moist, with a very large surface area and a rich blood supply. You need any two of those which would give you the mark. I like, the idea of the thinness of these walls is that you've got a short diffusion distance. The gases don't have to travel far to diffuse in and out. And that's what you're writing in here. So you could even say that there's a short diffusion distance. That works for absorption of and diffusion. Anyway, you've got absorption and diffusion. So you could use that. You could reuse that at GCSE as well. It's a good answer. Short diffusion pathway. You can have a high concentration gradient. So there's a lot of carbon dioxide in the blood, not a lot in the air, so it diffuses out. There's a lot of oxygen in the air, not a lot in the blood, so it diffuses in. So that's why you have that rich blood supply. Anything that explains, or describes, sorry, two of the features. Oh, look, physics. The distance time graph shows Ellie's cycle ride. So she's on a bike. Here's the distance in miles. Here's the time in minutes. Got to be aware, do we have to convert or not? And there's 10 little bits, little divisions in our scale. Okay, right. So the question is, how far did she cycle? How far did Ellie cycle? Let's look at the distance. So let's go up. Where's the top of the graph? There. If I move across 3, in between 3 and 4, that's 3.5. That's 3.5. That would be C then, wouldn't it? There we go. There is 3.5. 3.5 miles. Yes. Put an X on the part of the graph where she was travelling at the fastest speed. Well, speed is the steepness, and we call it the gradient, don't we? The gradient of the graph, so the steepness. The steepest gradient is where she goes fastest, and it is that section there. You could put an X on it, like that, or you could put an X next to it. I'd still understand, but we're really looking at this section, and as long as it's clear, you get the mark. So an X on the part of the graph is that part, steepest. There's the air pollution question, this one. Which diagram shows the products of combustion of a fossil fuel? Now, you're water, soot, carbon dioxide, carbon monoxide, depends how much oxygen you've got present, and something else. And we know the missing gas that causes acid rain. So it says, which gas causes acid rain? It's sulfur dioxide, which is D. Sulfur dioxide dissolves in water, creates acid. One problem when soot is produced in a combustion. Okay, so soot. If you've got asthma, you might know about this, behind a stinky lorry or something. Soot is a respiratory irritant. It can cause all sorts of breathing problems, and it can damage the lungs. So soot can cause lung damage, cause irritation, and if you've ever seen old photos of London, also you'll see that the buildings get blackened because the soot sticks to them. And many years ago, London was absolutely black. All of the buildings are black with soot. They've been all cleaned now, but I remember actually those buildings being cleaned when I was younger. So it can blacken buildings, but also damage the lungs and cause breathing difficulties. Explain how gases in the atmosphere can cause the greenhouse effect, and describe one problem the greenhouse effect may cause. Okay, so we've got a command word, which is the word explain. So how does it do it? Well, the carbon dioxide, or you could say greenhouse gases, because it didn't specify carbon dioxide. Carbon dioxide is a greenhouse gas, so you sort of bracket. I said greenhouse gases, I probably should put that. The greenhouse gases, like methane, like carbon dioxide, can trap heat and absorb energy. So as the sunlight warms the surface, it radiates out infrared radiation. Those gases absorb that infrared radiation, warming up the atmosphere, and that is can lead to global warming because of the increase in energy that's trapped by that layer of atmosphere above the surface of the Earth. So it absorbs energy. This can increase temperatures globally, and that can lead to an increase in temperature of the atmosphere, which leads to global warming, and that can, of course, contribute to climate change, or it's agreed by scientists at the moment. The majority of scientists think that there is a human contribution of that absorption to climate change. Good. The melting points and boiling points of 4 elements in the same group of the periodic table are given in the table. Give the state of an element at room temperature. That's given you 25 degrees Celsius. So we're going to remember that groups go down and periods go across. So 4 elements in the same group. So it's the same pattern going downwards. State is solid, liquid or gas, and we're going to put it in the last column. Sorry about the lines in my print, but that's the way it is. So minus 220, and it boils at minus 188. B melts at minus 101, C melts at minus 7, and D melts at only 144. So let's look at the boiling points. Looking at the boiling point, that's definitely going to be a gas. That's definitely going to be a gas because that's long evaporated. That one is a liquid because it's melted, but it's not boiled. But that one's going to be a solid because it's neither melted nor boiled because 25 degrees Celsius. If I looked, some of that I looked at the middle, like in between. They're definitely a gas, but that's the answers there. The table shows how 4 metals react when heated in air: gold, copper, mercury, sodium. And it sort of explains how they react with air. Well, they obviously react with oxygen, aren't they? And it gives you a pattern. And sodium, it says, immediately bursts into flame. That's exciting. Explain which of the 4 metals is least reactive. Well, it's the one that reacts most slowly. And copper is slowly, but mercury is very slowly. But gold doesn't change at all. And in terms of speed, that's the slowest then. So gold doesn't change at all. It's unreactive as a metal. So we're going to write gold as it does not change when heated in air. Give the names of 2 metals that are more reactive than mercury. Mercury says very slowly forms a red powder. What's faster than very slowly? Slowly and immediately. Slowly turns black and immediately bursts into flames is very much quicker than very slowly forms a red powder. So it's sodium and copper. Let's put that in. Good. Complete the word equation for the reaction when mercury forms the red powder. Now it's obviously reacting with oxygen in the air, isn't it? So we've got mercury plus sign means reacts with. So we're going mercury reacts with oxygen to form mercury oxide. If you're old, you might remember it as mercuric oxide. But mercury oxide. If you put mercuric oxide, I'll probably give you the mark because historically that's what it used to be called. Question 10. The diagram shows an outline of the periodic table. Which letter shows the location of the non-metals? So on the right-hand side here, we've got the non-metals. And on the left of that step, you can see the dark step shape. You've got the metals on the left-hand side, and B is hydrogen. So which is the block of them? So A, B, C, or D? It's the right-hand side. It is D, because it says metals plural. So it is D, isn't it? Non-metal there. Tick. Which box shows the chemical symbols? Sorry, these 2 boxes. The boxes show the chemical symbols of 2 metals. What's the name of Al? Aluminium. And A is sodium. Sodium. Sodium comes from the old name natron. That's its old name, but we call it sodium in English. And we've got another reaction. Iron is a metal that can be burnt in oxygen to form iron oxide. Complete the word equation. Iron reacts with oxygen to form iron oxide. That's so easy. I'm not going to spend a lot of time on that one. A chemist burns 0.8 grams of iron in oxygen, and it reacts to form 1.1 grams of iron oxide. Calculate the mass of oxygen that reacted in the iron. Because of the law of conservation of matter, we've got this reaction. Iron reacts with oxygen to make iron oxide. What's the addition? So we take 1.1, which is your final product. We take away the 0.8 grams, and that leaves us with 0.3. So 0.3 grams, there it is. There's the answer. Easy peasy. Sam runs a 100-metre race in 16 seconds. This is a speed calculation. There you are. Calculate how fast he was running. This is maths. As soon as you get the word calculate, calculator time, it's maths. Speed is distance divided by time. That's the distance, 100 metres. The time is 16 seconds. We divide 100 by 16. And let's put some calculating in there. 100 divided by 16 equals, put it in the calculator, that comes out at 6.25 metres per second. Joe runs a 100-metre race in 14 seconds. Is Joe faster or slower than Sam? Explain whether Joe was faster or slower than Sam. Explain. Okay, why? How do we know? Let's have a look. So we've got an explanation. Well, if speed is distance divided by time, and the time is less, then Joe is running faster because he's covered the same distance but in a shorter time. And if speed is distance divided by time, then your speed value will be higher. You could put the numbers in a calculator yourself and prove it to yourself. It's definitely true. Joe is faster in 14 seconds over 100 metres than 16 seconds over 100 metres. So you got the word because you've got an explanation in there. Sally runs 10 kilometres, which is 10,000 metres, at an average speed of 3.5 metres per second. What does average speed mean? Is it the longest distance divided by the shortest time? Total distance travelled divided by total time, shortest distance divided by longest time, or total distance times total time taken? And of course, it's the total distance travelled divided by the total time taken. Next question. When 4.9 grams of magnesium is burnt, 8.1 grams of product is formed. Well, that means we've added something to it. What's the name of the product form? Well, it's burnt, so it's reacting with oxygen in the air. So it must be called magnesium oxide. Magnesium reacts with oxygen to form magnesium oxide. Let's find it. It is there. Magnesium oxide. Explain the increase in mass. Well, we don't create or destroy matter in a chemical reaction. The atoms don't get destroyed. We're adding them on in this case. So we've got the magnesium bonding with the oxygen to form magnesium oxide. That mass of oxygen atoms is being added to the mass of the magnesium atoms that are already there. We're taking them out of the air and bonding them to the magnesium. So if we put in there the 8.1 minus 4.9, that comes to 3.2 grams of oxygen being added to the magnesium oxide, to the magnesium to form the magnesium oxide. So we can say that much oxygen was added to the mass because it reacted with the magnesium to make the magnesium oxide. And because the atoms are not created or destroyed, then, or I should say because the atoms are not destroyed, that's why it didn't go down, the mass would go up, or the mass increases. It was added to and increased. Let's write that down. That's a technically difficult question. You've got to remember the law of conservation of matter. Question number 13. The apparatus, we've seen this, as used to show what happens during the combustion of a hydrocarbon fuel, and that means they could ask you any part of this apparatus. Look, so the gas gets taken through there, goes through cobalt chloride paper, lime water, conical flask with thermometer. Right. What will happen to the thermometer reading during the experiment? Well, it's an exothermic reaction, isn't it, when something burns? So does it say the temperature increases? Temperature increases because the energy is transferred from the fuel to the surroundings. It decreases or increases, and the reason. So B is the only acceptable because it's transferred from the fuel to the surroundings. What will happen to the lime water? Lime water is the chemical test for carbon dioxide. It goes from clear colourless to cloudy or milky white. So which one? It's not going darker. Nope. Is it going cloudy? Is it turning pink? It's C. C's the only answer there. Why will the cobalt chloride paper change during the experiment? So why? Well, when we burn any fuel, that's hydrocarbon or organic, paper, wood, that sort of thing, and there's good amount of oxygen, we make carbon dioxide and water. The carbon dioxide is tested by the lime water. The cobalt chloride paper tests for the water, and it goes from blue to pink. So we're saying what happens, and just off the page there, let me bring the camera up, is because the answer's A. The cobalt chloride paper will turn pink because the water is produced in the reaction. That's the answer. During the experiment, a black powder can form on the funnel above the candle. That's true. That's soot, isn't it? Oh, the question says name the black powder. Well, that's really easy, isn't it? It's soot. Why does it form, though? That's a bit more difficult. The black powder is soot, but it forms because of incomplete combustion. That means there's not an adequate amount of oxygen. There's not enough oxygen in the air for complete combustion to take place. If we had complete combustion, it would be a clean flame that produces only carbon dioxide and water. Incomplete combustion gives you carbon monoxide and soot as well. So it's formed when there is insufficient or not enough oxygen for complete combustion. That's how we describe that. As long as I can understand what you're talking about with a lack of oxygen, oxygen starvation is sometimes the name of it, then I would give you the mark for that. Plants need light to make glucose. Name the process which makes glucose. Ah, yes, a reference to question 1. It's photosynthesis, isn't it? I think this is just checking that you know the name of the reaction. It didn't ask you specifically, but we know now. Photosynthesis. And what's the word equation? The word equation for photosynthesis. And in the mark scheme, by the way, it says do not accept misspellings. So you had to write photosynthesis. In the space below, write the word equation. So we've got carbon dioxide and water, and they react together. And it's light energy that gives energy for this reaction to happen. And we're going to form glucose and oxygen. So you write carbon dioxide plus sign, water, arrow, glucose plus sign, oxygen. Because on the left the plus sign means and on the right reacts with, and on the right it means and. Oh, we get to plot a graph. A student walks from home to shop. She walks 240 metres. It's 6 minutes at steady speed. Good, that means a straight line. She waits at the shop for 3 minutes. Then she runs home at twice her walking speed. Draw a distance time graph. Use the axes in the graph on the below. Good. So we've got distance on the left, time on the bottom, and so we're just going to go 240 metres in 6 minutes. Twice the walking speed, which is going to halve it. So we'll put that in mind. So 6 minutes, 240 metres. There. Okay. Then she waits at the shop. So straight line, because it's a steady speed. She waits at the shop for 3 minutes. So let's count along 3. 1, 2, 3. There we go. Put across there. And then twice the speed. Good, because we haven't got much space left on the graph. That's a big clue. So this is the waiting time. Then we're going to take it from the waiting time, and she's going to go back home. So we're going to do that 1, 2, 3 along there. Let's connect the dots. So there to there, there to there, and there down to there. Ta-da! Right. Calculate maths. As soon as you calculate, it's maths. Distance divided by time and all that jazz. What's the total distance, though? We're going to add them up. So she's going to walk how far? She's walking to the shop, which is, 240 metres? And then she's going to walk back from the shop a further 240 metres. So she's 240 metres there and 240 metres back. Add those two together. She travels a total distance of 480 metres. Using your graph, calculates the student running speed in metres per minute. Speed is distance divided by time. So let's see if we can find these values. What's the distance divided by time? Or here. So what's the distance? From there to there, 240 metres, isn't it? 240 metres. And it took 3 minutes. 3 minutes. Okay. 1, 2, 3. So it's in metres per minute, so that's quite handy. We don't have to do any conversions. 240 divided by 3, put that in the calculator, comes 80 metres per minute. So, gentle jog, I think. Ooh, I've seen this picture before. The drawing shows some of the cells found in the tubes inside the lungs. Explain why. That's a how command word. Explain how these different types of cells, so we've got the goblet cells producing mucus and cilia, and we've got ciliated epithelial cells, and they do the wafting, don't they? So the cilia waft all of the dirt and the muck and the bacteria and the viruses and the pathogens, all of the stuff you don't want in your lungs, out into your throat to be swallowed or spat out, I suppose, but removed out of the lungs. So it's one, cilia sweep the mucus out of the lungs. What makes the mucus? It's the goblet cells, isn't it? It would have been made more sense if I'd have started with goblet cells in this answer, thinking about the goblet cells make the mucus, which is sticky. So the pathogens, the bacteria, the microbes, how would you call it? The bacteria, viruses, fungi, pollen, stuff like that. It sticks to the mucus, and then the cilia wave it out. I did it that the cilia wave it out, and it's produced by the goblet cells. Either way round, it's fine. Mucus is made by the goblet cells, which is sticky to trap dust, germs, pathogen, pollen, bacteria, viruses, fungi. What else did I call it? Any of those sort of keywords. Microbes, microorganisms, that sort of thing. Yeah, there we go. They're the two parts. 3 metals, X, Y, and Z, are heated with the metal oxides. This is called a displacement reaction. And you've done it with the halogens, I think. So we've got metal X, metal Y, and metal Z. If the metal is more reactive, it'll take the oxygen from the less reactive metal. That's how it works. So if you get a reaction, that means that the metal's going to take it away and react. But if there's no reaction, then it's not strong enough. So we're going to try and derive from this a reactivity series. So we're going to try and get an order of reaction here. So a more reactive metal will react with the metal oxide, strip the oxygen away, and you'll get a reaction if it's reactive enough. That's what we're going to do. If it's not reactive enough, it can't do that, so you'll get no reaction. So let's look at the pattern. So we've got no reaction when metal X reacts with Y, but it does get it with Z. Y with X gets a reaction. Y with Z gets a reaction. Interesting. And metal Z, you get no reaction and no reaction. Okay. Let's put this in order then. Right, so metal Y, no reaction, no reaction. Okay. So that means that the metal, the oxide, it can't take anything. So that must be the most reactive, because oxygen can't be taken off of Y at all. Z, you get a reaction and a reaction with X and Y. That means it's the least reactive. Oxide of metal X, so metal X is a reaction, no reaction, is in the middle. So it is Y, X, Z. Y is the most reactive, Z is the least reactive. That's the end of the test. Wow, there we are. Good job. Excellent. How did you do?
Mr. Marsh review hit different, no cap. Now the reflection sheets on my lap.